So here's another example of a type of problem you'll be given. Prove that the sum of a series, equals some explicit formula here. Now the problem we looked at in the first overview was we tried to prove that the formula for the nth term of a sequence was something, and now we're actually looking to prove that the sum of a series is something. So what I might want to do is look at the first partial sums here and see if I can see this pattern, although fat chance, that looks pretty complicated. It's a cubic. It's a complicated cubic. I don't think I'm going to see that pattern, but you never know. So if we try, it's pretty easy. What they're telling us is the sum of the first n squares. So what does this series look like? Pretty simple. 1 plus 4 plus, let's see, 9 plus 16. And we might want to convince ourselves that this formula works because it looks suspiciously complicated. But let's see, we're out here at the fourth term. 4 times 5 is 20. 20 times, let's see, 20 times 9 is 180. 180 over 6 is 30. 1 and 4 is 5. 5 and 9 is 14. 14 and 16 indeed is 30. Was I likely to stumble across this formula by looking at this is n equals 1, n equals 2, n equals 3, n equals 4? Not likely. But the good news is someone says, hey, here's the formula. Prove it to me. And again, proof by induction, two parts. I need to show true for n equals 1, and then that's one part. And the second part is assume that if true for some n equals k out there somewhere, then true for n equals k plus 1. So for that second part, I want to assume that my formula is true for the kth term. So it's the sum of the first k out to k is k plus 1, 2k plus 1 over 6. Assuming that if that's true, then the sum of the first k plus 1 terms then is going to be replacing a k everywhere with k plus 1, k plus 1, k plus 1 plus 1 is k plus 2. 2 times k would be 2 times k plus 1, so that would be 2k plus 2 plus 1 is 2k plus 3 over 6. So this is what I need to show. If this is true, I need to show that's true. And our strategy again is to look at the two left sides and to note that they are very similar. This side and this side differ only by that k plus 1 squared term being added here. So if this is true and I add k plus 1 squared to each side, I'm going to get a true statement. So if I go ahead and add the k plus 1 squared over here to this side, I then need to show that this simplified right side, this mess here, plus k plus 1 squared equals this mess here. And that's where the algebra comes into play. So if I go ahead and add and I'm going to be looking now just at the right sides here. If I go ahead and add that k plus 1 squared to both sides up here, adding it to this right side is going to give me a k plus 1, 2k plus 1, all over 6, plus k plus 1 quantity squared. And I need to show that that equals this mess here, simplifies, and can be expressed as this. Because if I've done that, I've shown that the formula works when I plug in a k plus 1, when I go from the kth term to the k plus first term. So the question is, how do I simplify this and turn it into that? So again, I've got to show those right sides equal. You might want to go back just again, make sure we want to show the right sides are equal. Here's the sum of the first k terms. Add that k plus first term to it. That's the sum of the first k plus 1 terms, and by formula, it's supposed to equal, replace the k with k plus 1, replace the k with k plus 1 with k plus 1 plus 1, replace the 2k plus 1 with 2 times k plus 1 plus 1. The formula is supposed to yield this. Does this equal that? And the question is, simply solve using a little algebra. I got to find clearly a common denominator here, which would be 6. So multiply top and bottom, k plus 1 squared over 1 by 6. Got my common denominator. I then note that I can factor out a k plus 1 out of each of these two terms. And when I do that, I factor the k plus 1 out, I'm left with a k times 2k plus 1 plus 6 times one of those k plus 1s. Expand, and I get to here, and then go ahead and rewrite as a quadratic this second expression here, 2k squared plus 7k plus 6 over 6. Does that indeed equal k plus 1, k plus 2, 2k plus 3 over 6? And it does, because this expression here factors to exactly what I need. I kind of knew it has to if I've done my arithmetic and algebra right. K plus 1 times, let's do it actually consistently, times k plus 2 times 2k plus 3 all over 6 equals ditto. And again, just check it. Let's see. K squared, k times 2k is 2k squared. 4k and 3k is 7k. 3 times 2 is 6. So indeed, I've shown that if the formula is true for for n equals k, then the formula also is true for n equals k plus 1. So thinking of my ladder analogy, I can get from one rung to the next rung on the ladder. And if I can get to the first rung, and I can get from one rung to the next rung, I can get from 1 to 2, I can get from 2 to 3, 3 to 4, etc., etc.